Okay. All right, welcome everybody. We're very happy to have Marcel Corchado-Abello to come and give our colloquium today. He is a third-year student at the Astrophysical and Planetary Science Department at the University of Colorado, Boulder, and he works with Dr. Maria Kazachenko, studying the magnetic energy evolution during flares, using primarily space-based observations. Originally from Puerto Rico, he completed his bachelor degree in physics from the University of Puerto Rico, Mayaguez, in 2020. And most of his favorite activities revolve around food, cooking, eating, and watching people prepare, and of course, sharing it. And we're very pleased to have Marcel here. He was here as a source student for many years, or several years, at HAO, and so it's great to see you come back. Welcome. And you're going to be talking about inferring fundamental properties of the flare current sheet using flare ribbons, oscillations in the reconnection flux rates.
Yep.
Take it away.
Thank you so much, Sarah, for the presentation. And it is great to be back here where I think I really started understanding solar science through the source program. So it's been a while, but very happy to be here back. Yes, as Sarah mentioned, I'm going to be presenting this topic of inferring fundamental properties of flare current sheets using flare ribbons. This is work done by me and Maria Kazachenko as part of my PhD at the University of Colorado, Boulder. So the first thing that we're going to be seeing, that we're seeing right here, is a picture of a limb solar flare. Maybe you are seeing it. So
is it playing?
In my screen, it's playing. I wonder if it's
Stepping back and forward. No, the movie.
Oh, the movie. Sorry.
Oh, there you go. There's the arrow.
Okay. So it is. So the movie itself, though, it's showing.
There you go. Yeah.
Okay. Hopefully, it is for everyone. Okay. But basically, what you see there in that image or that movie here, some observations from the AA instrument, and it's looking at the evolution of a solar flare. So I'm going to play it again and identify a few things that we can actually see in this observation. So the first thing is we see this sudden brightness lower in the solar atmosphere, and that corresponds to a flare. There was an ejection of material that also corresponds to a coronal mass ejection, or CME. And after the fact of this initial brightening, we start to see also these loop-like structures kind of like appear in the solar atmosphere. And we see that they're still connected into the solar atmosphere down into the photosphere, where I've identified there some foot point regions. And all these structures are going to be very important in our understanding of really how reconnection is happening here in the solar atmosphere, where basically all these flares are happening. So moving into the talk itself, our main science question that we're going to be elaborating in this talk is whether or not there are observational evidences of reconnection in flares occurring as a bursty oscillatory process. I'll go into details about that. And whether or not these bursts are associated with dynamical processes occurring in the current sheet. Now, throughout the presentation, what I'll be presenting is these novel results or new results where we've shown that magnetic reconnection flux is actually evolving in a way that displays these oscillations and also compare it to the relationships with particle acceleration. So throughout the talk, going through some introductional remarks, just about basic information that you need for this presentation. What are flare ribbons? Kind of like the standard model of flare. Some information about magnetic reconnection. Then we'll dive into data that we're using, or methods to analyze it. Go into a little bit of basically what the results that we're getting for a few single events, going into details of how that works. And then also present some statistical results of this 73 flares survey that we've done. And then we'll end it. So, going to the introduction. So as I showed before in that little video, I've talked about the flare. So the flares, as most of you probably already know, here in the room and maybe talking here. The flare is really this, the way that we describe it from the observations is the sun and localized emission of light that really encompasses the full electromagnetic spectrum. Because it encompasses such a broad range of emission in the electromagnetic spectrum, we know that there are many physical processes interplaying here and contributing to the emission of the flare. One of the very important things to really understand here is that most of these processes and other stem from the fact that magnetic energy is being converted to different types of energy. An example being the particle acceleration, heating the solar atmosphere, both motion of coronal plasmas, like in the coronal mass ejection. So, moving forward, one of the things that we use to understand a lot of what's happening with flares is actually these observations of flare ribbons. And the ribbons, they try to show up there, are local enhancements of the chromospheric emission. And these are actually due to the precipitation of energetical particles from up in the corona during the flare into the solar chromosphere or lower atmosphere of the sun, where density is high enough that it can actually, particles can collide and actually produce irradiation. And in relationship to what's happening with the coronal magnetic field or the magnetic field in the sun, the flare ribbons really correspond to the foot points of these reconnected loops or these flaring loops as we've shown in the previous image. And now I'll show a little animation of this, play it, probably see it. And here in this little animation, the flare ribbons would be, you're not seeing it in the...
Yeah, there's a lag, it seems.
Yeah.
I'm not sure why.
Yeah, I've been seeing it for all of them, but I don't know what's happening.
There
you go. So the flare ribbons is these bright structures that you're actually seeing move or expand from what would be this line dividing different polarities of the magnetic field. And this emission actually corresponds to the foot points of the newly reconnected magnetic fields. So, to understand this connection or elaborate on it a little bit more, one of the tools that we'll be, or frameworks that we'll be using, is the standard flare model, otherwise known as the CSHKP model. We'll get there. There we go.
About 10 seconds.
Yeah, and so for people here online, you'll hear me talk about something and maybe wait for a couple of seconds just to see it show the display. So the first thing that we'll notice about the standard flare model is it's a model for flares happening in this eruptive scenario. What I mean by this eruptive scenario is that in this model framework, we actually have this flux rope that rises and actually is ejected from the solar atmosphere, which is what we call the CME. Although this is not going to be the focus of the talk or our project itself. Rather, we're interested in what's happening below that flux rope, and basically here in this region where reconnection is happening. So as the flux rope rises, it stretches out this region of current that also has enhanced currents. Such region we call the current sheet. In that region, magnetic reconnection happens, and as you see in the little picture, it encloses the magnetic field of the flux rope, forming the CME, but it also forms lower into the atmosphere these other sets of magnetic loops, which are what I've been referring to as the flaring loops. Now, during this process of reconnection and afterwards, what happens is particles in that region where the reconnection is happening are accelerated, and they are propagated down into the atmosphere through those coronal loops or flare loops. And when the particles actually collide with the chromosphere, as I mentioned before, they deposit their energy and they emitted a broad range of emission. Particular for this project, we care about the UV emission, hard X-ray emission, which is what we see or are using to actually observe both the flare ribbons and also the episodes of particle acceleration through the hard X-ray emission. Afterwards, we also see, as part of this framework, that the material that has now been, where this energy has been deposited, is heated, and that heated material actually rises through the flare loops and emits in soft X-rays and UVs. And that's what in that initial figure we actually saw as these expanding flaring loops that kind of like showed up after the initial brightness. Now, I'm going to wait a few seconds, and we're going to be talking about magnetic reconnection. Okay. So just to start as we wait, the simplest scenario of magnetic reconnection is actually called, let's see.
Slide changing.
Yeah, it's very slow. The Sweet-Parker model.
You just get out of presentation mode and back in.
Yeah, let's see if that actually helps.
Try getting back in and out, see if it's better.
Well, that's way
No.
better. Oh, actually, no.
Always in presentation.
There we go.
Okay, it's a little bit better. I can also like not be in presentation mode if that
If
helps.
it comes down to it. Try moving it now. You might have fixed it. It seems like it's pretty fast. Try going forward. and backwards.
I just went
Okay.
forward. So
Oh, all right. Maybe not in presentation mode.
yeah,
That's okay.
we'll stay here.
Okay.
That's fine. You'll have a little sneak peek, but not too much. So simplest scenario of reconnection, or 2D reconnection at least, the Sweet-Parker mode. And as you can see here, the reconnection really refers to, very simplistically here speaking, when the magnetic field breaks and opposite pointing magnetic fields now reconnect and form new systems of magnetic fields or new configurations. And the simplest scenario, as I mentioned, is the Sweet-Parker model, which explains basically new magnetic field coming into that region here, which is the current sheet, where reconnection happens and being ejected here as these outflows of reconnection. And in this model, this happens in a very large system, very large current sheet. And the main idea is that it happens in a steady manner. So one of the main issues with this model is actually that the Sweet-Parker model explains reconnection happening in an order of, for flares at least, in the order of months, which is really not supported from the observations that we have of how flares actually evolve. We know that the flare lifetime ranges between seconds to hours. So typically, when we talk about reconnection models, we like to think about the inflow of, or basically like how new magnetic field enters that reconnection region, reconnects, that is dictated by that inflow speed. And typically for reconnection to explain flares, we need that inflow speed to be about 1/10 or 100th of the Alfvén speed in the corona. So from what I've been discussing, reconnection needs to happen a little bit faster than the normal Sweet-Parker model actually explains. So a faster scenario, oh, now it's slow here as well. Oh, okay, we're here though. A faster scenario of reconnection is what one such scenario is called the bursty reconnection regime. And in this regime, and I'll show that in this animation in a second, reconnection actually proceeds in bursts, which are modulated by plasmoids that exist within the current sheet structure. And these plasmoids, also referred to as magnetic islands, they represent this enclosed magnetic field structures, and they enhance the efficiency of reconnection. So over here on the right, what we're seeing is a CME model that also has some flares happening, where we actually see the plasmoid instability. And this is work from Benjamin Lynch and collaborators in 2016. So I'll play it first, and I'll be stopping it to see if it catches up. Okay. So the first thing that we see is this, all these blue regions correspond to current density in this 2D model. And we see that below we have a lot of current density. This corresponds to just a non-potential system that is going to eventually become the flare and CME region, so region with a lot of free energy. And we see here the start of the formation of the current sheet, that little structure over there. I'll play it a little bit more. The first thing that we see is as that current sheet actually elongates enough, we start to see the formation of these substructures, little enclosed almost bubbles or circles within that current sheet. And that's what I've been referring to as the plasmoids, magnetic islands. So we see that throughout the evolution of this reconnection, the plasmoids are being ejected from the current sheet, and they're being ejected both upwards and downwards. Now I stopped it here because in this model, you can see here on the right where my cursor is, we see the formation of another current sheet, and here the ejection of a CME, or a bigger plasmoid flux rope. It's going to be ejected and form that CME. And below it, we see something that looks very similar to our standard flare model. We see now the current sheet and this lower region of magnetic fields that corresponds to the flare loops. And what's happening here is this plasmoid instability, through which we see the evolution of many, many plasmoids being formed through the reconnection process and actually being ejected downwards into the flaring loops as well. Just finish playing the thing. Full evolution, maybe. You see the end. Sorry for the movies are not working.
No, it's. I think it's our interface. Sorry about that.
No problem. So now let's talk about a little bit about how do we connect reconnection to actual particle acceleration. Because we've been talking about these two ideas kind of a little bit. So the first thing to mention is, as I showed in the previous slide, we have CME models. A lot of them actually include this plasmoid instability in the current sheets. Therefore, in a lot of these models, like in the Benjamin Lynch one, we have reconnection happening in this bursty regime. Now, how do we connect that with particle acceleration? There's actually been a lot of work in numerical models, and mentioned a few authors here. Drake and Guidoni actually have both models, and Guidoni actually has a paper this year where she's using an analytical model, not just a numerical one, to actually show or suggest that plasmoids can actually accelerate particles, in this case ions, into the energy regimes you need to actually see afterwards, the hard X-ray emission, after they've exited the current sheet and actually hit the chromosphere. Another thing to point out is there might be some 3D effects in play. For example, when you actually include a magnetic field component that is now parallel to that polarity inversion line, that can actually affect or suppress the acceleration efficiency of these plasmoids, or these contained structures where particles can accelerate. And the last thing that I wanted to point out is some evidence about how the flare ribbon morphology can actually inform us about what's happening in the current sheet. And here we see, just wanted to point out that a lot of new studies looking into the fine structures of the flare ribbon fronts, specifically swirls and like wave breaking patterns that I'll be showing in a second, have been actually associated with plasmoids, or these magnetic island structures in the current sheets. In addition to that, there's been some new results actually connecting bursty modulations and the ribbon front widths to the actual bursty reconnection in the current sheet. So, last thing to mention here, there's a lot of evidence suggesting that the bursty reconnection scenario, driven by the plasmon instability, actually captures both bursty reconnection process, of course, and also the fact that we have particle acceleration due to these plasmoid structures. That's going to be a little bit of the framework through which our study actually goes. So, it's a reminder to everyone. In a second. There you go. So, this work, what we're going to be looking about is there actually observational evidence of magnetic reconnection happening through bursty oscillatory processes, and whether or not these bursts are associated with the dynamical process happening in the current sheet. So now we're going to move into our data. So for our data, we have a compilation of 3 different data products. First of all is just we use the SDO instrument, specifically AIA 1600, and IRIS slit jaw images in the 1330 and 1400 Armstrong filters to actually estimate the evolution of the flare ribbons. Specifically, we want to understand how the cumulative evolution of them, and we use these masks where you actually see that any new enhanced ribbon pixel will go into this cumulative mask M and form, by the end of the day, an evolution of how the full of the flaring pixels accumulate through the evolution of the flare. We use these, specifically the AIA ones, to actually estimate the reconnection flux. And we do that by just taking that mask and multiplying it by the, in this case, the vertical radial component of the magnetic field from the photosphere. So by doing that, we can actually estimate the magnetic reconnected flux that we usually can't actually observe through routine observations. And lastly, to actually get information about particle acceleration proxies, we use X-ray emission from both the GOES X-ray sensor and the Fermi gamma ray burst monitor to actually look at these events of hard X-ray emission and soft X-ray emission that are proxies of particle acceleration. So, in order to actually, with all those data products, describe periodicity, the thing that we're using is the AFINO method, which was developed by Inglis et al. In these 2 papers, 2015 and 2016. And the main idea is summarized here. You can look at the original papers for more details. But the original idea is you start with any given time series, and you normalize it, and you take out the mean. So you subtract the mean, and then you normalize it by the mean. You calculate the fast Fourier transform of that, so we're working in Fourier space. And then you have 3 different models for your data. The first model, MO, is a model of pure Gaussian noise, that constant value, and then a power-dependent component for that noise. And this is very common in a lot of astrophysical data. We have power loss in our noise, so-called colored noise. The second model includes the noise profile and then has a Gaussian enhancement in that Fourier space. And that Gaussian enhancement corresponds to when you actually have an excited oscillation. That's how we're identifying that. And then the third model, which is just a noise profile that has a break on it. So it's a more complicated background distribution for noise. Now, once we have our 3 models, what we actually do to analyze whether or not the fit is good, we use 2 things. The evaluation of goodness of fit using the reduced chi-squared, which you see there. And we also use the Bayesian inference criterion to actually determine which model is strongly favored. And here on the right, you have, as I was mentioning, the 3 different models that we have for our data. Model with the frequency-dependent noise, the one where you have the Gaussian enhancement, and one where the background actually has a break on it for the noise. So first data product that we use is the AI 1600s. And in this case, we're just showing some flare ribbons for an X-class flare. So I'll play it. You see it? You don't. But I'll stop at a specific moment. Yes, there we go. And what you see there is this is just a still, but you actually see these flare ribbons evolving. They're much more complicated than in the original 2D cartoon that I was showing. Now, one of the issues with this data is, although we are able to capture the full evolution, both in time and space of the flare ribbon, there's some saturation issues that make it difficult to describe, and also the lower resolution when compared to the second instrument that I'll mention in a second, that actually make it very difficult to observe fine structure details within the ribbon fronts. So to kind of work around that, we also include data by IRIS, the IRIS satellite. So IRIS provides very comparable observations, but in this case, they have a smaller field of view and higher resolution. So this is for the same flare. And again, I'm going to play it first. Maybe you see it, maybe you don't. And then I'll stop it in a second to just show some details. You see the stopped image. So as compared to before, when we actually look at this image, we actually see that within that region that looked not smooth, but smoother, we actually see that there's a lot more details happening here. So when I was talking about finer structures within the flare ribbons, this is an example of kind of like those wave breaking patterns here in the ribbon front. And I'm going to try to capture a moment where we actually see as well the formation of some swirls. So that's what I'm going to be referring to as finer structure details. So now I'm going to jump into the results of our study. And first, as I mentioned in the beginning, we're going to go through just a couple of example events, just to show more detail how we actually compare the flare evolution to the reconnection rates and the hard X-ray emission. And then I'm going to move into some statistical results from our sample of 73 flares. Okay. In a second, I will catch up. Okay, there we go. So the first result that we're going to be talking about is comparing the reconnection flux and rates to the evolution of the flare ribbons. So in this figure here on the right, we have 3 panels. So the one on the left is going to be showing black and white, just show the vertical magnetic field at the photosphere. And this is an active region, very complicated, very nice. And then on top of that, we're going to see the evolution of the flare ribbon mask with time. It's going to be color-coded with that bar over there in the bottom. Here we're going to be tracking the evolution of the flux, the reconnected flux, and then the reconnection rate in the bottom. So I'll play it and probably won't watch it moving, so I'll just stop it here at the end. You can actually see a lot of the details. Basically, because it's color-coded, it's nice, because even though we're not seeing it moving, we get the same information. That's nice. So the main thing to get from here is that we see using, these are ribbons extracted using AIA, So the 1600 filter. So we see that the flare ribbons actually evolve. The evolution looks almost smooth. Looks like it's actually just expanding and moving along away from the polarity inversion line. There's some big and structured things like these hooks and all this sort of stuff. But overall, as I mentioned before, because of the lower spatial resolution, we actually don't see all these fine details. Yet, the evolution of the magnetic reconnection flux, we see here, it also seems pretty smooth. It just accumulates as the flare ribbon expands and moves along and sweeps away new magnetic field. But when we look at the time derivative of that, which is what we're calling the reconnection rate or the reconnection flux rate, we actually see that that evolution is actually happening through bursts. And we see it here. Go to a few of these images. But basically, that the addition of new magnetic field into that's being swept away by these ribbons actually is happening in these bursts. You're not seeing it move along. That's fine. Okay. So now, in terms of how these bursts try to compare them with some of the fine structures that we're actually seeing in the iris observations. So it's a lot happening in this plot, but let's start here with the first burst. So when we see a burst in the reconnection, we actually see that throughout the evolution of this whole bursty profile, we see that the flare ribbons actually have these fine structures. In this case, I pointed out a few, like this wave breaking patterns, swirls associated with the second burst. Maybe the third burst also have some, maybe a little bit of both swirls and wave breaking patterns. And this is just to show that these structures that have been associated with the plasmoids in the current sheet actually are showing up in our data when we're looking at the evolution of the reconnection budget. Specifically in events where we actually see the reconnection budget evolving in a bursty manner, which is to be expected if we're having plasmoid-driven or plasmoid unstable current sheet. So now we compare these results of the reconnection rates with hard X-ray emission. There you go. Specifically, again, this is a proxy for particle acceleration. And now we're looking at a different M2.1 flare. And we see here is on the top, we're seeing the Fermi data from channel 0 to 50 kiloelectron volts there. In the middle, we see in black the soft X-ray emission, and in blue and green, you can actually see the derivative of that, which is a proxy also of hard X-ray emission. Sorry. And you can see that specifically for the 15 to 50, so those two upper level channels in this specific plot, green and yellow, you actually see that where the bursts happen in the soft X-ray derivative matches pretty well with the hard X-ray emission, and this is to be expected via the Newport effect. And in the bottom, we actually see the evolution of the reconnection rates. And in this case specifically, we see that they have a periodicity of about 3 minutes. Now, the burst in the hard X-ray emission, you can see that little arrow, maybe those dotted lines, is actually delayed from the burst in the reconnection rate. So you can see it here, that whenever we have not whenever, but specifically for these larger bursts later in the evolution of the flare, the reconnection rate burst happens first and then follows burst in the hard X-ray emission. So one question that we're very much interested is, specifically for you as well, because I've been showing these plots in normalized, is actually how much flux is getting reconnected in each burst. And specifically, we find in this event, we have 11 bursts, showcase here. See the little black line there. And the main thing here is that from each of these bursts, let me go back a second. Each of these bursts, what we do is we take the flux from the difference between the end of the burst lifetime to the beginning, and that way we actually estimate the total reconnected flux that's been associated with a given burst. And with that, we produce this little histogram. It's going to show up in a second. And what we see is for that 11 bursts in the event that I've just shown, the reconnection budget for the burst actually corresponds to about 0.1 to 7, second it'll show up, times the 20 Maxwells. There we go, which is seen here in this histogram here, distribution of those. And to put that into context, what this means is that the bursty part, or each one of those bursts, actually accounts for when you add them all together, to 75% of the total reconnection budget for that given event. Now, one of the questions that we might ask ourselves, specifically when compared to simulations that I showed at the beginning from Benjamin Lynch, is whether or not each one of these bursty episodes that we're seeing in our observations actually corresponds in this framework to a separate plasmoid or island, magnetic island, being ejected from the current sheet, or whether it is actually the combination of many islands colliding and merging, eventually being ejected, or many islands being ejected, that actually form these bursts in our reconnection rate. So, make a little stop here just to summarize some of the results that I've been talking about. We're moving forward to the statistical stuff. See? So, now it's taking more than before.
I know, it's slowing down. I'm not sure why. I wonder if it's worth unplugging the owl.
I don't know, it might, but I have no idea. Keep it
Or
on
can
this.
you disconnect and reconnect to the meeting? That doesn't make a difference.
No idea.
Huh, there's some screen. Can somebody online, Annie just texted me that she doesn't see his screen. Are other people having trouble? Are you all seeing the same lag that we're seeing in this room? Okay, she sees the screen.
Okay,
Yeah, there's
yeah.
a delay. There's something going on, which is very odd.
Yeah.
Okay.
Yeah, that's fine. But we're here.
We're here now.
That's fine. So discussion point, how do we interpret the flare ribbon analysis that we've done in reconnection rates to some of the information that I've been talking before? So we see that this fine structure that I've been talking about, specifically for the AAA data, we're not really seeing it. Yet it contributes to the modulation of the ribbon front with, as I mentioned before, and I showed, this wave breaking patterns, all this stuff, that actually contribute to what we're actually seeing with the AAA data, which is larger bursty evolution of the flare ribbon area. So the little image, basically what's happening is that the flare ribbon is moving, sweeping up new magnetic field in a back bursty manner. And that is what gives away to the reconnection rate burstiness. We also see, just as a reminder, that these swirls and wave breaks, referring to as fine structures, have been associated, connected to the plasmoid structures in the current sheet. Furthermore, that the modulations of the flare ribbon widths have actually been associated with the bursty reconnection, and also with co-temporal and spatial hard X-ray emission. So with the acceleration of particles in a bursty manner as well, which is also kind of what we've been seeing in our data. So now we move forward and going to be talking a little bit more of the statistical results. So this I can just say before the slide shows up. So for our analysis, we've included, additional to the ones that I've shown, there's 73 flares, out of which 39 are C-class flares, 24 are M-class flares, and 10 are X-class flares. And the notation, if anyone is unfamiliar, from C to X, it increases with energy. So the X ones being the higher energy flares. Okay. So, oops. No, now it's gonna wait. Okay. So here on the right, what I'm showing is just the y-axis. We have the periods of the reconnection rate oscillations as detected or as actually modeled by AFINO. And in the x-axis, we're seeing the goodness of fit statistics, which is the reduced chi-square. So first thing to notice is that most of the data, the periods range from 1 to 11 minutes, and most of the data is actually close to reduced chi-square of 1, which means that the using this quasi-periodic model for the oscillations is actually produces fairly good fit. Now, in terms of actually determining whether or not the quasi-periodic pulsation model is the preferred model for the data, this is where we use this Bayesian inference criterion, and what we are determining to be a event that has a preference of the oscillatory model over a noise background one is when this Bayesian inference criterion difference between them for two models is lower than -10. And you can see it here with all these yellow dots. So from the previous image, I've just included here the 26 events that show the QPP model being the preferred one. So now we can ask ourselves, we saw in the data that there were bursts that kind of look very similar to the ones in the reconnection rates in the hard X-ray emission. Specifically, now we're going to be talking about the Fermi ones. In this compilation of plots, we see similar to before. Now just comparing the reconnection rate period with the Fermi reconnection rate period in the 5 different channels that we've included in our analysis, going from lower energy emission, the hard X-ray, to higher, being 100 to 300 kiloelectron volts. So the first thing that we see is, and I'll show in a second when I just show the detections, sorry, is that there's a lot fewer detections of QPPs in the hard X-ray data using AFINO than when compared to just the reconnection rates. We do see, and here, doesn't here, I can actually zoom in a little. There is some correspondence between the periods that are below 5 minutes, which is these little lines here in red. They just show the correspondence that there is for the QPP periods and the hard X-ray periods. And we see that there is some correspondence specifically for the lower energy channels between the two periods. Yet, as you can see from the actual results of the, when we actually do the linear fits and we get the correlation between them, they're mid-correlated for most of them, maybe the exception being 15 to 25 kiloelectron volts. And when we actually see the higher energy channels, these are constrained by the fact that we have few M and X class flares. We see that in general, there are way less events emitting in these higher energy bands. And overall, we see that the detection of a QPP in the hard X-ray emission, in this Fermi data, is inconsistent across the energy channels. And that's going to be maybe a little bit more obvious in this next slide, where we're actually just seeing the detections. Maybe not. It's very, very, very bright. Yeah, you can barely see.
I can see it, but you have to move your head.
Yeah, yeah. In the room, it's going to be hard. Maybe online, you have better luck. But basically, showing that the detections very inconsistent across the energy channels. Okay. So we do the same thing with. Okay. We do the same thing with the soft X-ray rates from GHOST, which is, again, a proxy for hard X-ray emission using the Newport effect. And we see, again, there's no detection of QPPs in this data. They include the same information. That's because the two GHOST bands are very close to each other. And therefore, also, we have a little bit more consistency of the periods across the both energy channels. And again, for lower period events, we do tend to see some correspondence, but correlations are low. And here are the detections, 4 and 7. Okay. Okay. Do it. Okay, so just to interpret these results, we see that the magnetic reconnection rates can actually be represented with the QPP model 26 times out of the 73, thus suggesting that there is some quasi-periodic processes modulating the burst and the reconnection. And also, we see that in the case of the periods of the X-ray emission, both in the Fermi and the GHOST data, we see that only a few are actually consistent with the periods in the reconnection rates, though there are some there is some evidence to also suggest that there are oscillatory processes there. Yet the AFINO methodology fails to characterize a lot of the oscillations in the X-ray data. You have two more slides to go. You can do it. Okay. So, as I mentioned before, when we were looking at the few events, we saw that there was some delay. Just to summarize the slide, we see in general that for the 73 events included here, we see that overall there is a 24-second, which is this black line here in all the distributions. We see that the Fermi emission is, the distributions are centered there with a peak at 24 seconds. So all of the Fermi emission is statistically saying, you can see that in average, it's delayed by 24 seconds in our study. This 24-second is very interesting because it actually corresponds to the cadence of the instrument, but we did some analysis looking at different time derivatives for our data and found that it wasn't a systematic issue. So that 24-second is actually a product of the data. We see here the same thing for the soft X-ray emission. In this case, what we see is that the distributions are not as nicely centered, or don't have such a nice, peak in the distribution. But overall, we see that the reconnection bursts come before the soft X-ray rate peak burst by about 0 to 48 seconds. So again, this is consistent with the Fermi data where we found it to be delayed about 24 seconds. So just to interpret these results, delays in the hard X-ray emission have been studied before, but there is no agreed upon or explanation to why the hard X-ray emission is actually happening delayed from the reconnection rate bursts. And this is something really for future investigation as to why this is happening. So now I'll just present the conclusions. So in general, we find that the magnetic reconnection, as described by the reconnection rates derived from flare ribbons, actually occur in these bursts, oscillations. We found 26 of them that actually could be fitted with the QPP model. And we found that the periods of those range from 1 to 11 minutes. When comparing the first Fermi and ghost data, what we actually see is that there are some bursts in the emission of X-ray material. So this is a proxy for particle acceleration. But we see that they are usually delayed from the reconnection rate burst by a couple of seconds up to a minute. The high resolution iris data actually showed that there are a lot of fine structures that are actually modulating the flare ribbon fronts, and these are evidence of, or have been suggested to be evidence of, the plasmoid instability in the current sheet. So what we suggest is that the nearly cotemporal QPP bursts in the reconnection rates and the hard X-ray emission show up eventually.
There it is.
Okay, perfect. This is what I've been talking about. Yes, so we suggest that this nearly cotemporal QPP burst or oscillatory burst in the reconnection rate and our hard X-ray emission is evidence of oscillatory processes happening in the reconnection region, and that plasmoid dynamics actually are turning, leading the reconnection process to happen in bursty episodes that actually also translate into bursty particle acceleration. And this work will be submitted into APJ in the future. Okay. That's the end of the presentation, but before dropping off the mic, I just wanted to thank Sarah, Masumi, and Cheryl from inviting me to give this talk. Everyone here, really thank you for bearing with a little bit of the technical issues, but I hope that the science is very clear. And yeah, just to thank everyone, family and friends, for showing up and just also helping me out, and people from my group and colleagues as well. So thank you very much for paying attention, and hopefully everything was very clear. Thank you.